Okay, so in this video, we will solve the following linear system, again in 3 equations and 3 variables in x, y, z. As always, the first step is to construct the augmented matrix of the linear system. The first row, and here be careful, since there's no y, then its coefficient is 0. Think of this as being x plus 0 times y minus 3 times z. And so the first row becomes a 1, 0, negative 3, negative 3. Second row, 2, negative 5, negative 1, negative 2. And the third row, 1, 2, negative 5, 1. We start with the leftmost column and try to introduce a leading 1 in the top row. Well, it already is there. And then we kill the entries below it. So we will do row 2 minus 2 row 1. And we will do row 3 minus row 1. Since we are only changing the second and third row, we will recopy the first one. So 1, 0, negative 3, negative 3. Let's apply the 2 row operations. 2 minus 2 is 0. Negative 5 minus 0, negative 5. Negative 1, negative 2 times negative 3 is plus 6. 6 minus 1 is positive 5. Negative 2 times negative 3 is again plus 6. 6 minus 2, positive 4. Let's apply the second row operation, row 3 minus row 1. 1 minus 1 is 0. 2 minus 0 is 2. Negative 5, negative 3 is negative 5 plus 3, negative 2. 1 minus negative 3 is 1 plus 3, positive 4. Well, we have our leading 1 in the top row. We've killed all the entries below. So we ignore the first row, the top row, and we repeat. From the leftmost column, we try and get our second leading 1 in the top row. Well, we can't make a 1 from 0, so we move to the next column. There are 2 non-zero entries here, and so we can do though. Well, how do we get our leading 1? Well, we could multiply row 2 by negative 1 over 5, but that would give us a fraction here. We can perhaps try and do this. We could, and there are 2 ways here, we could multiply row 3 by 1/2. Since every term here is divisible by 2, there would be no fractions. And then we could swap row 2 and row 3 to place the leading 1 in the top row. Or we could be sneaky and do row 2 plus 3 row 3, as 5 plus 6, as negative 5 plus 6 would be positive 1. Just for the hell of it, let's do this. So row 2 plus 3 times row 3. What's nice about this one is it's a single row operation, whereas with the other option of multiplying this by 1/2 and then swapping these 2 rows would have us do 2 row operations. This is a bit more sneaky, but sneaky sometimes is good. So we recopy the first row, we're not changing it. We can recopy the third one, we're not changing it either. And now let's apply this row operation. So 0 plus 0 is 0. Negative 5 plus 6, positive 1, which is our new leading 1. 5 plus 3 times negative 2, 5 minus 6, negative 1. 4 plus 3 times 4, 4 plus 12, 16. Now that we have our second leading 1, we want to kill the entries below it. And so quite simply, we do row 3 minus 2 row 2. Let's apply this operation and see what comes out. We are only changing the third row, so we can recopy first the first 2. Let's apply the row operation now. Row 3 minus 2 row 2. So 0 minus 0, 0. 2 minus 2, 0. Negative 2. Negative 2 times negative 1 is plus 2 is also 0. And 4 minus 2 times 16 minus 32 negative 28. And now if you notice, the third row is all zeros, but the constant term isn't 0. And I claim this is interesting. Why is this interesting? And this is something that you always have to watch for. A row where all the coefficients are 0, but the constant term is not 0. Let's see why this is interesting. Let's go from the row of the augmented matrix back to the corresponding equation. So this would be the equation 0 times x plus 0 times y plus 0 times z equals negative 28. Now think of it, we are asking to solve the corresponding linear system, which means that we have to find a value of x, a value of y, and a value of z that satisfies the given equation. But think of it, no matter how you choose x, 0 times x is 0. No matter how you choose y, 0 times y is 0. And no matter how you choose z, 0 times z is 0. So for any choice of x, y, and z, the left-hand side of the equality is 0, but negative 28 is not 0. So the equation has no solution. No matter which real values you choose for x, y, and z, you will have to satisfy the equation 0 equaling negative 28. This is impossible, and so the linear system cannot be solved, therefore it has no solution. So you always have to be on the watch for this potential problem. And this is the only way to have no solution, where every coefficient is equal to 0, but the constant term is not 0. This will always imply that 0 equals a non-zero number, which is not possible, and will always therefore imply that the linear system has no solution. And that's it. We tried to solve the system, but there is no solution to be found, and that is our conclusion. Now, there's a technical term for a system that has no solution, and the term is inconsistent. So we see the linear system is inconsistent. Same thing as no solution. So if you ever say a system is consistent, then there is at least one solution. If we say the system is inconsistent, then there is no solution. So if you had a really large linear system, and early on the row reduction appeared a row of 0 coefficients and a non-zero constant, you can stop. You don't have to reduce any further, as this will always imply that there is no solution, therefore the system is inconsistent. So it is impossible to find any solution, as there are none.